Hello and welcome to my 14th lecture on operating system development, and today I'm going to be talking about, basically what I talked about last time and what does that imply, because there are obviously problems related to multitasking, in the sense that when you have multiple processes and you're doing some sort of preemptive context switching, there are going to be different scenarios that you wouldn't usually have to deal with in a monotasking operating system. And obviously it is immensely valuable to talk about those things, at least from a slight theoretical perspective. So the first thing that I should sort of mention is that processes can obviously be split, as the average viewer should probably know, into threads. And those are tinier tasks that are done which compose an entire process. So a process is split into multiple sort of threads. Obviously you can have one thread, which is for a given process, but many processes might require many for different things that it will be doing. And then, for example, those threads could, for example, but don't have to be, given to different computational units. And there are obviously certain problems that arise with resource allocation because, well, by this point, we're sort of aware that you can allocate resources to different processes, as in you have this process abstraction, and you can just use that process abstraction in order to save the information about the different resources that will be allocated towards this process. Now, we don't really want to waste such space in saving all those information. It's not even just wasting, it's by design the sort of idea that all your threads are going to have shared resources that the process has access to, right? So you have some process P1 and you have some process P2, and this is going to be split into some threads. So is this. I have no idea whether I should index this 1 and 2 as well, because it belongs to P2. Let's just, So we have this, and obviously those processes are going to have their own sort of information about what resources are allocated to them, and they're going to have separate resources allocated, but the threads are going to have the same shared resources. Obviously, splitting processes into smaller tasks like this is very useful, and you schedule them or you deal with them, and it makes for a very generally elegant system. But it obviously also creates some problem related to having to deal with a resource that is shared, and that is obviously going to generally cause some trouble. And anything that I'll be talking about, which relates to threads, is going to also generally apply to processes, because processes can also have some shared resource, right? So even though they might have some resource of their own, there might be some resource which we're going to share. And shared resources and this sort of preemptive multitasking mechanism that usually appears in operating systems, it's not really a good pair of things. It will cause a lot of different problems. And probably the most infamous one is the critical section problem. So the critical section problem appears when we have some threads or some processes with a shared resource. And obviously we're going to execute some instructions. We imagine for this box to represent, the series of instructions that this thread or this process is going to be executing. And we have some sort of resource which they share. And it can obviously execute some code. Well, usually threads and processes, they execute some code, just generally computational sort of code, as in you simply, perform calculations, you store the results in registers, you do things like that. That's a lot of what the processes or threads are doing. But it will also go into those I/O bursts, where it will perform input or output operations. So at some point it will go into some sort of I/O burst. Now similarly, T2 will also go into some I/O burst at some point. Now imagine that we're executing these two threads or these two processes, and we have some sort of preemption. So at a given point, we imagine that we're going to stop execution, we're going to save a context, and then we're going to load that context later. So imagine we're doing this I/O burst, and let's say both I/O bursts are related to this one shared resource. So I'm just going to say that those are processes because I'm generally used to working on processes a bit more, but that's just for my comfort. So P1 is a process that's being executed, and at some point over here, it's starting to write to this resource or read to this resource. It doesn't matter, but we're having some sort of I/O interaction with this resource right over here. And let's say that somewhere in the middle of this, we either get some sort of interrupt or whatever preemption mechanism we have, and the time that was allocated for this process has run out, and thus it will now be allocated to the other process, and let's say the process is P2. And P2 is also going to have this I/O burst which pertains to this, and is going to start executing it. So it is going to so this is sort of preempted into this, and we get here, and this over here tries interacting with this resource. Now, what if this was writing? What if it was writing a sequence? And what if this tried to read some sequence? Well, we can obviously see that we can get some sort of corruption. None of the processes will sort of obtain from the resource what they wished for. And well, in the case of trying to write to memory or something, it's whatever. But if you're trying to perform some printing jobs or whatever, or something more similar to that, just generally more complicated input-output operations, it will cause a lot of trouble when one process hasn't finished everything related to input and output related to a process, but because of a context switch, another process starts doing that. So you can see that overriding and all things like that will generally occur if you find yourself in that sort of scenario. And because of that, those two fragments of code of two processes with a shared resource that pertain to the same shared resource are going to be called their critical sections. And the fact that a preemption could occur and another critical section could start while the other has not ended, leading to data corruption, overriding, and failed operations, is called the critical section problem. So how can we deal with that? How can we sort of solve the critical section problem? And the general answer is to use synchronization primitives. So synchronization primitives, right? So I already sort of superficially talked about the fact that you have inter-process communication, processes that can communicate with each other. Obviously, threads also have the ability to sort of give each other some information, and we can use this information wisely in order to synchronize them together. So we can let the other processes know what a certain process is doing, such that we avoid things like the critical section problem because they're all synchronized, they're all nicely synced up. So a fundamental synchronization primitive that sort of everything stems from is something called semaphore. So semaphores, if you don't know, well, in the modern days, they're the sort of the equivalent of traffic lights on the railway. But that's only because we have semaphores that are sort of like with lights nowadays. Because earlier in the days, the word semaphore used to represent different systems of generally managing. Well, I only know it in sort of this railway context where it was used for managing all sort of railway traffic. And ensuring that no collisions between trains happen and so. But you can generally associate a semaphore with something like a traffic light. I might be wrong on this, but I think that in Spanish, I think a friend once told me that a traffic light is simply el semaforo or something like that. I might be completely getting that wrong, but something like that. So you can generally associate it with a traffic light, and I think it's a good association because we're going to have different states that are going to let different sort of processes move or wait at a given time. So really managing, this access to resources is a lot like sort of traffic management. So it can be generally associated with traffic lights. And a semaphore works in a very simple way. Well, a semaphore, let's begin with the fact that this is simply a natural number. It's some non-negative integer, which is going to be shared between two processes, which is usually going to be titled S for semaphore. So we're going to have some sort of non-negative integer, or even natural number, so you could say that we're going to have some S belonging to a set of naturals. And we're going to have two functions. We're going to have a P function and a V function. So both of those are from Dutch, because the P stands for probeer, and V stands for verhogen. I probably butchered that, but this means to try, and this means to increase or to increment. I think it just means to increase, right? Because Holden, sort of like German. So this is going to increase our variable over here, and this is going to actually decrease it. So the sort of usual English names that are given towards those functions are wait and signal. Right, so the idea is that the semaphore is going to be the number of the units of a resource that is still available, in the sense that that's how many processes or how many threads can still interact with this resource such that it is safe, such that we can, you know, comfortably assume that they're allowed to do that. So, for example, let's say that number was initially 2. So we have some process P1, and it says, hey, I want to interact with this resource that has 2 available units. Let's say we also have P2 and P3, right? So P1, it wants to try to get this, and what it rigorously means to try, to probieren, that's why I don't really like the English wait, which is why I introduced the Dutch version, even though I don't like, I mean, it's not that I don't like Dutch, I don't know Dutch, but I really like that it's called probieren, like try, because it's going to try to get a unit of that shared resource. So what it rigorously means to try is that it is going to check, well, it is actually going to wait, which is why the English name is also okay. It will wait till this value is not 0. So till, you know, something is available. Well, here it is not 0 at all, so it doesn't have to wait at all. So what it will do after waiting, or here not waiting at all, is it will decrease this value by 1. So now this value is going to be 1, and it is going to perform some operation. Like, let's say it was some memory. It is going to write to that memory, and let's say it's still writing to that memory, while P2 says, hey, I also want to do something with that resource. So what it does is it calls P again, and it waits until this is not 0. Well, it's not 0, it is 1. So what it does is it decreases that semaphore value over to 0. So P1 and P2 are using that resource, and P3, it also wants to try to use that resource. So it calls P, and the value of the semaphore is 0. So what it has to do is it has to wait. So it's waiting, and while, you know, the semaphore is equal to 0, and at some point P1 finishes everything that it needed to do with this resource. And thus it signals, you know, that, hey, you can use this now. So it signals by verhogen, by increasing that value. So the value is increased to 1, and now P3 sees, okay, I don't have to wait anymore, this is 1, and thus, since it's called P, you know, and in that P function it is waiting, it can now decrease it to 0 to let other processes know that P3 is now using this. Isn't this such a simple yet elegant solution to process synchronization? It's a very beautiful synchronization primitive, in my opinion, where we have this natural number semaphore, we have this probieren or waiting function, and we have this verhogen, the signaling that we're done with using this. So yeah, so that's basically it. So now P2 and P3, they have a copy of this resource, they have a unit of this resource, and P2 at some point is going to say, I finished, So it's going to call V, so it's going to increase it by 1 to let other processors know there's a unit available, and then P3 is going to finish using it, changing the value back to 2. So that's the general idea. So V, very simple function, increase, increment the semaphore, so we increase it by 1, and then probier, we are going to try to get a unit of this resource, and we're going to wait till there's some unit available, so till there's not 0, and then we're going to decrease the value to let know that we're using it. So that's how a semaphore works, and this sort of provides some sort of solution to our critical section problem, because whenever we have a critical section, we can simply say, we're going to have P of S, we're going to do our critical section, and then we're going to do V of S. So we're going to wait, we're going to do our critical section, and then we're going to signal that there is a unit of this resource available. So that's a semaphore, and this is a very fundamental synchronization primitive in the sense that pretty much all other widely used synchronization primitives stem from the semaphore, because you have something called a lock. Now, a lock is very similar, except this time we're simply going to have a Boolean value, right? You have some L, which is a Boolean. And we have some two functions, they're still usually called P and V. Except this time the only thing we're going to do is P is going to it's simply going to change the value to 0. If the value is 1, it's going to wait until the value is 1, and when it's 1, it's going to change it to 0 to tell the other processes that this is taken. And V is simply going to, get it back to 1. So it is very easy to see that a lock is simply a special case of a semaphore. In fact, it's often called a binary semaphore, because it is identical to a semaphore, except you just start with a value 1, right? And 1 is the maximum value that you attain. So instead of this non-negative integer, we consider a Boolean, just a Boolean value. That's a lock, that's a binary semaphore. It is used a lot because I'd even say that probably in the majority of resources, maybe that's an overstatement, but in a lot of resources, only one process or one thread will be able to use it at a given time. So a binary semaphore is going to be a very common solution because of the fact that one is going to say, "Hi, I'm using this. Everybody else don't use it," and then it's going to signal that now you can use it, and another one is going to use it, and such. So it's going to be mutually exclusive. In fact, this whole problem is, all the synchronization primitives, they're all sort of related to this problem of mutual exclusion, where we have some resources which are going to be mutually exclusive in the sense that, we will not allow for multiple processes to use it simultaneously. We're going to mutually exclude each other, and there's actually, people usually shorten this problem of mutual exclusion to simply mutex. And what's funny is that mutex, it refers to this whole problem of mutual exclusion, but it is also considered a synchronization primitive. And a mutex is a certain object in through many environments that is a lock that can be shared between different processes. So we usually consider for a lock to be, instantiated and released by a single thread, whereas a mutex is an object which could be instantiated by one thread and released by the other. So that's basically, the problem of mutual exclusion and synchronization primitives. And I could say, yeah, cool, now we have some way to communicate, so we don't really have to worry about a critical section probably anymore. But fear not, because there's obviously way more problems, way more problems that arise. There's a lot of problems that arise, even when you have synchronization primitives. Because life is not so simple. And a very common problem that appears in operating systems, and in fact it's a huge, I'd say, area of study in operating systems, as in if you were going to read a book about operating systems, there's probably going to be a whole chapter dedicated to this, and it's a deadlock. So, a deadlock is a certain situation, very inconvenient situation, where, well, let's draw an example. We have some process P1, we have some other process P2. Obviously, there are more processes that could generally be engaged in a deadlock. And we have some sort of resource, I will call it resource 1, and we have some sort of resource 2. And let's say that P1 currently owns a unit of some resource 1. So this process has this resource at the current moment, and let's say that it has performed some lock, or by the use of some semaphore, and it doesn't currently allow for any other process to use this resource. Now, analogously, let's say that P2 owns a copy over here owns a unit of this resource R2. So it owns a unit of R2, it holds it in the sense that there is a lock which disallows for another process to to take this resource, to use it. And let's say that P1 actually wants to use R2 while it holds R1. So R1 is locked, and it is going to be waiting for R2, because we remember when we have synchronization primitives, when we have the semaphore, right, we have this waiting step. We're waiting for this availability. It's usually a while loop, and the process doesn't care about anything else. So we are holding a resource, and we are waiting for this resource R2. And R2, P2, let's say it's never going to actually let P1 get R2, because it is constantly requesting to get a unit of R1. So what happens in this situation is P1 has locked R1, it is holding it in this rigorous sense, and then it is waiting. It's usually in this sort of infinite loop where it's trying to wait for a resource that is locked, that is not going to be unlocked, because P2 would only stop locking this, it would only stop holding R2 if it was given R1, which is not going to be given because P1 is holding it and it's waiting. So both processes, or, well, in a more complicated deadlock, even more processes are constantly waiting for each other, and nothing is ever going to move. And, they both stop doing anything. They're just waiting for each other, and they're not executing any other instructions. So that's what a deadlock is. We're in this sort of cycle over here. So obviously it's good, we've sort of briefly described. I've briefly described what a deadlock is, but it's good to know the actual conditions, the rigorous conditions that have to occur in order for a deadlock to happen. And the first condition that is usually given is that there is no preemption. Now, what this means in our context is that you can't just snatch a resource. You can't perform a preemption on a resource. And this condition makes sense. And the thing is, you usually don't have to check for this condition in the sense that you only have to know once that the operating system implements it that way or not. So it's not a thing you have to check for every possible scenario. You just check it once for the operating system. Does the operating system allow processes to just snatch resources from each other? If that is the case, well, then obviously there is no problem. There might be, different problems related to then what happens to those resources and such, but it's not a problem of a deadlock anymore. Nothing's dead, nothing's locked. We might have problems occurring if processes are just going to be, preemptively taking resources from each other, but it's not a deadlock per se. So the second condition that has to be satisfied is mutual exclusion. So I think mutual exclusion makes sense. It's a condition that refers to a certain resource. And it says that, well, if one process is going to own the resource, then another process cannot. And, well, this is obviously a condition, because if both P1 and P2 can have a resource, then there is no problem in this scenario over here, because P2 is just going to use R1 while P1 holds it. If this resource is not mutually exclusive, then a deadlock is not going to occur. So we have no preemption, we have mutual exclusion, we have a hold and wait. So what this means is all the processes that are supposedly in a deadlock, that are supposedly in a deadlock, they have to be holding some resource, as in this resource is locked and they're holding it in the sense that they're currently waiting and there is nothing that will let them release this resource. And they're waiting, for another resource to obtain. Right? So we're holding and waiting, both P1 and P2, and if there are more processes, all of them would have to hold and wait. And the fourth condition is this wait has to be circular, so we need a circular wait. Because if it was just hold and wait, then whatever, at some point it could, release this resource, right? It could give back a unit, but no, it cannot because of the circularity of this scenario, of this situation. So for a deadlock to occur, we need no preemption from the operating system. We need mutual exclusion. So the resource has to be mutually exclusive. It can only be given to a given process at a given time. We need some hold and wait, so all the processes need to be holding a resource, and they'll be waiting for another resource, and there needs to be a circular wait. So this wait of hold and waiting has to be circular. How do you resolve those deadlocks, right? Because, well, one important thing is obviously deadlock prevention. You should obviously not generally let processes get in a situation where this occurs. but it will. So it's good to prevent deadlocks, but then you actually have to resolve them once they happen. And the first sort of thing is deadlock detection, right? Because to solve something, the operating system has to be even aware of the fact that a deadlock has occurred. Detecting deadlocks is a problem of graph theory, because I think it's not really difficult to see that this way that I have drawn the processes and the resources, it highly suggests that this is simply a directed graph where the processes and the resources are the nodes of the graph. So in order to detect a deadlock, you generally have to find a cycle in a graph and see if this cycle happens with some resource which is mutually exclusive, and this should generally be enough, right? Because you have a directed graph, so you can easily see that from a resource to a process it's going to be holding, and then from process to resource it's going to be waiting for some resource. You're going to be detecting a cycle, you're going to check for those conditions, and you can generally detect a deadlock within an operating system. And then how do you resolve this? Well, usually I have to use some relatively drastic methods in order to resolve the deadlock. The most popular deadlock resolution methods are by murder and by theft. And yes, both sound relatively brutal, don't they? And that's because they are. They usually have quite some dire consequences, but yeah. So solving a deadlock by murder is, I think, relatively obvious. You have to kill off one of the processes, usually the least important, like for example with the lowest priority, just like that. Well, this is a relatively simple scenario, but in a deadlock with more processes, you have to determine the process which will actually resolve the deadlock, which is often called the centroid of the deadlock, or at least that's what I've been taught. Because I had to solve those things with a lot of processes on paper. So if there are a couple of processes and they both resolve the deadlock, then you kill the one with the lower priority, but obviously you want to kill the one which will actually resolve the deadlock, which is usually the one that holds the resource that the most processes are waiting for. So the one whose resource has the highest degree node of the graph, right? So if you were to kill this process, P1 over here, then, well, this solves all of our problems, because now P2 has a unit of R2 and it gets a unit of R1, because P1 is not holding R1 anymore because it doesn't exist. We've killed it. So P2 gets the resource at 1, it does whatever it wants, and it functions normally, and everything is great. So that's how you can resolve the deadlock, by the way of murder. And the other way you can do it is by theft. And in order to do it by theft, what you do is you consider the resource. Usually it's the resource which, if you have more processes, again, it's the one which is within the cycle the highest order node of the directed graph. In this scenario, well, both generally have the same degree, so it doesn't matter which one we take away. But what we simply do is we say, hey, P1, you can't do this anymore, you can't use that one anymore. And P2 is simply going to steal this resource R1 from P1. And P1 is going to do whatever it wanted, and everything is great. And in the best possible case, what can happen when you resolve deadlocks by theft, which is not always possible, sadly, is that P2 finishes doing whatever it was doing with R1 and R2, and it actually frees up a unit of R2. And you can then, once it no longer wants R1 because it has finished some operation, P1 can actually get a unit of R2, and P1 can properly execute. But in a majority of cases, this will not be possible, because since P1 was requesting R2 while R1 was locked, it means that it was probably doing something relatively important with R1. So when R1 is simply going to be taken away, it is probably going to cause for the process to completely malfunction, and it is probably going to crash in some way, shape, or form. So deadlocks, as you can see, they're generally inconvenient, and one can generally encounter them in their daily lives, and it is not nice. You know, a program can just freeze and it can eventually just die out entirely, right? So that's something that happens even modern operating systems, right? And is a relatively big unsolved problem. Unsolved problem in the sense that there is still not a good solution for both preventing deadlocks and actually solving them in a way such that no processes, are guaranteed to, such that all processes are guaranteed to survive, right? I answered a comment recently about how I said that I'll try thinking through my sentences more and try not to rephrase them, but I'm definitely struggling with that. So, that's the general idea of what a deadlock is and how you can resolve one. Sometimes doing it by murder, it at least prepares the environment for the fact that P1 is not going to try to get the resource back when it's going to try to malfunction. And sometimes it's just better to kill it off instantly. Right, so those were some considerations pertaining to preemptive multitasking that will generally occur, so you have to deal with threads, so splitting processes into tinier tasks, and then those threads will have shared resources. There are problems with shared resources. There's the critical section problem. How do you solve it with synchronization primitives? But they don't solve things because there are other numerous problems in operating systems, such as deadlocks. Yeah, but there are some general ways to deal with those, even if they don't sound the best. So yeah, I'm really happy with, I guess, this video and the previous one, because I've talked about some things which I consider to really be at the heart of the operating system, because generally, you have all those resources. I've talked about how you have data, and you have memory, and you have I/O devices. But what's really important is that they're given to processes. And the processes were given yet another resource, were given CPU time, but giving the CPU time in a multitasking preemptive environment it creates a lot of different problems. And the way you manage those processes, the way you give them the resources, the way you plan out how they're going to be executed, the way you're going to be solving problems, like I explained, with resources being allocated to different processes. I think that's really at the heart of an operating system, and I consider that to be really beautiful. So I'm really happy with how I talked about CPU time and scheduling and context switching and process abstractions, allocating different resources to processes and for what problems arise with that. So all things user space. But I still am not done, because it might seem like we've constructed some sort of process abstraction and different things pertaining to that in the user space. And we already have processes which function, they're scheduled, they're given the four resources which I talked about, which were CPU time, data, memory, and I/O devices. But there's still one thing that I haven't talked about from my first lecture. And I'll be talking about that in my next video, which will be the final one of the series. So I'm really excited to record it, but I'm also a bit sad. But I also, whenever I'm sad, I remember, well, I said that I'll only have 15 lectures for a reason. Well, I didn't specifically say 15 lectures, but I limited myself to a certain scope, which I talked about in the first lecture for a good reason. I mean, this whole thing took me almost a year and a half, and I don't know if, over time I'd lose motivation or whatever, but I really wanted to produce a complete series of what I consider to be the most important fundamental things in operating system development. And the only thing that's left is in the definition that I have provided. I said that those processes, those operating system managers, the resources and such, but it allows the user to comfortably run those processes. We're lacking some sort of shell, some sort of graphical user interface. And even when you have that, how can you sort of improve your operating system? How can you make it go from this fundamental thing to something which is more modern? How do I define modern? What do we expect from an operating system? What does the user expect, right? Those will be the things that I'll be talking about in my final lecture. So I hope I'll see you in that one.